Welcome to Endocrinology. Today, we are going to explore one of the most fascinating and crucial communication networks inside your body, the DAG-Calcium signaling system. Imagine your cells are like highly secure fortresses. Messages from the outside need a way to trigger massive, coordinated actions on the inside without ever breaching the walls. This pathway is exactly how that happens. By the end of this video, you will understand not just the biology of this system, but the mathematics behind how cells listen to hormones. Let us dive in. To understand how this signaling pathway works, let us start with a simple analogy. Imagine you are the manager of a large, complex factory, but you are permanently locked outside the building. You need the workers inside to start building a specific product immediately, but you cannot go inside to tell them yourself. Instead, you press a special button on the outside wall. This button sends a spark along a wire, which then splits into two distinct signals. One turns on a loud siren, and the other flashes bright red lights. Together, the siren and the lights tell the workers exactly what to do. In the human body, hormones act just like that manager. They cannot enter the cell, so they trigger a split signal system inside. Now that we have our analogy, let us look at the actual biological players. The DAG-Calcium signaling system is used by many water-soluble hormones. Because these hormones can't cross the oily cell membrane, they bind to a specific G protein-coupled receptor located on the outer surface. Think of this receptor as the button on the outside of our factory. When the hormone binds, it activates a specific stimulatory G protein called GQ. This GQ protein then travels a short distance along the inside of the membrane to activate an amplifier enzyme called phospholipase C. This enzyme is the crucial spark that will soon split our signal into two powerful messengers. With phospholipase C activated, we reach the critical moment where the signal splits. This enzyme acts exactly like a pair of molecular scissors. Its specific job is to find a membrane lipid called PIP2 and cut it into two crucial active pieces. These two pieces are diacylglycerol, which we call DAG, and inositol trisphosphate, which we call IP3. This cleavage is the biological equivalent of turning on the siren and the flashing lights. One original hormone message has now been translated into two distinct internal messengers, each with its own specific and vital job to perform inside the cell. Let us follow these two messengers to see how they change the cell's behavior. The IP3 molecule travels deep into the watery cytoplasm until it reaches the endoplasmic reticulum. Here, it acts like a key, opening calcium channels and flooding the cell with stored calcium ions. This sudden spike in calcium is a massive internal alarm. Meanwhile, the DAG molecule stays anchored in the cell membrane. It waits for that newly released calcium to arrive. Together, DAG and calcium activate a powerful enzyme called protein kinase C. Once activated, protein kinase C goes on to phosphorylate other proteins, fundamentally changing the behavior of the cell to match the original hormone's command. Before we look at the mathematics of this system, we must understand why it matters in real life. Without the DAG-Calcium signaling system, your body would lose the ability to perform rapid, life-sustaining functions. For example, if you are bleeding, a hormone called vasopressin uses this exact pathway to make your blood vessels constrict, preventing severe blood loss. Similarly, the hormone oxytocin uses this pathway to trigger the powerful uterine muscle contractions needed for a mother to successfully give birth. It is also the primary way your brain tells your pituitary gland to release other essential hormones. If this system fails, cells become completely deaf to critical commands. To understand how a cell knows when to trigger this pathway, we use the receptor occupancy equation. Conceptually, this formula bridges the gap between the amount of hormone in the blood and the strength of the resulting signal inside the cell. In this equation, Y represents the fractional occupancy, which is the percentage of total receptors currently bound to the hormone. The symbol H in brackets represents the concentration of the hormone outside the cell. Finally, Kd represents the dissociation constant. This constant measures how tightly the hormone binds to the receptor. A lower value means a stronger fit. As the hormone concentration increases, more receptors are occupied, driving Y closer to 1, which means total occupancy and a massive internal signal. Now that we have our formula, let us apply it to a real clinical scenario. A patient in labor has a circulating oxytocin concentration of 4 nanomolar. The oxytocin receptors on her uterine muscle have a dissociation constant of 1 nanomolar. We need to find the fraction of occupied receptors to see if the signal is strong enough for effective labor. We chose the receptor occupancy formula because it directly relates these given values to cellular activation. We substitute 4 for the hormone concentration and 1 for the dissociation constant. Adding the denominator gives us 4 divided by 5. The final answer is 0.80. Physically, this means 80% of the receptors are bound, ensuring a massive activation of the signaling pathway. Following the receptor activation we just calculated, the cell releases calcium. To measure the true strength of this internal alarm, we calculate the fold increase in intracellular calcium. Conceptually, this tells us how much louder the signal has become compared to the quiet resting state. In this simple formula, F represents the fold increase. CF is the final stimulated calcium concentration after the channels open, and CI is the initial resting calcium concentration before the hormone arrived. If the final concentration goes up, the fold increase F becomes larger, indicating a much stronger biological response. It is crucial that both concentrations are in the exact same units before dividing. Let us see this calcium spike with a concrete example. Before stimulation, a cell's resting calcium is carefully maintained at 100 nanomolar. After IP3 opens the channels, it spikes to 1.5 micromolar. We're asked to calculate the fold increase. We use our fold increase formula, but first we must address a critical issue. The units do not match. We convert the final concentration from micromolar to nanomolar by multiplying by 1,000, giving us 1,500 nanomolar. Now we can safely divide 1,500 by the initial 100. The final answer is 15. Physically, this means the calcium levels increased by a massive factor of 15, which is exactly the dramatic shift needed to trigger muscle contraction. Now that we have calculated the signals, let us look at the entire pathway visually. In this diagram, you can see the cell membrane at the top. Notice the hormone binding to the G protein-coupled receptor on the outside. Follow the arrows inside. The receptor activates the GQ protein, which in turn activates phospholipase C. You can clearly see phospholipase C acting on the membrane liquid PIP2, splitting it into DAG, which stays at the top, and IP3, which travels downward. Look at the bottom where IP3 binds to the endoplasmic reticulum, causing calcium ions to flood out. Finally, follow the arrows from both the calcium and the DAG. They converge to activate protein kinase C. This diagram beautifully summarizes the split signal concept we have been discussing. We have covered a lot of ground, so let us reinforce the most important ideas from this topic. First, remember that the DAG-Calcium signaling system is a vital biological relay race. It translates an external hormone signal into powerful internal action without the hormone ever entering the cell. Second, the critical step is the cleavage of the membrane lipid PIP2 into two distinct messengers, IP3 and DAG. Third, these messengers work together. IP3 floods the cell with calcium, and DAG uses that calcium to activate target enzymes like protein kinase C. You have now mastered both the biology and the mathematics of this pathway, understanding exactly how tiny amounts of hormones can save lives. Great work.